Good afternoon, everyone. Welcome to the 2011 Nyquist lectureship. My name is Jong Han. I'm the chair of the Electrical Engineering Department. The Nyquist, or the Harry Nyquist lectureship, is named in honor of one of our distinguished alumni, Harry Nyquist, who graduated or received his PhD in 1917. And he had made really fundamental, foundational contribution to the field of electrical engineering. On the backside of this pamphlet, there's his bio. I'm not going to repeat, but in one of the citation it said that his work in thermal noise analysis, data transmission, and later that was developed into Shannon-Nyquist theorem, as well as his study of the stability of control system in a negative feedback, and that became Nyquist criteria. So for those of us who are electrical engineers, these are very, very well known in the foundations. So in 1969, he was awarded the National Academy of Engineering's fourth Founders Medal in recognition of his many fundamental contributions to engineering, and this lectureship is in honor of him. And I should also emphasize this lectureship was made possible through a generous gift from another engineering alumni, J. Robert Mann Jr., and he and his wife, Mrs. Mann, are with us today. He is a class of 1951, and currently he's a chairman and the CEO of EJ Electric Installation Company, and founded in 1899, so it's entering the third century for this company. And he, over the past decades, he is a very strong supporter for Yale School of Engineering and Applied Science, as well as the Department of Electrical Engineering. He has, just give a few examples, he supported the J. Robert Mann Center for Electronic System Design and for the Faculty Innovation Fund for Electrical Engineering, as well as more recently, a very nice student center, and this is a J. Robert Mann Jr. Engineering Student Center. Normally, for this type of symposium, we have a reception at that a very nice center, but for today, because of there's a renovation work, so later the reception will be outside the Davis Auditorium. So this is by way of announcement. He is a recipient, so Mr. Mann is the recipient of the Yale Medal, and this is Yale's highest award to honor outstanding individual service to the university. And we just want to express our appreciation for his long-time support. For today's speaker, so I feel I'm taking half of the talk now. So for today's speaker, it's an honor and a pleasure to have a Professor John Rogers here with us. He is from University of Illinois at Urbana-Champaign. For those of you who are at the lunch, forgive me, I'm just repeating some of his career. He grew up in Houston and went to UT Austin and received a bachelor's degree in '89, so you can get his age. And then then he went down to MIT and received a PhD in physical chemistry in '95, and after that, he spent 2 years as a junior fellow at Harvard, and then decided to try something different and spent 5 years at Bell Lab. The first 3 years, according to him, was really a marvelous time, and the second half, the latter 2 years, in 2000 and to 2002, that's a post-bubble era, so that made him decide to try the academia since 2002, and currently he is the Lee J. Flory-Founder Chair in Engineering at Illinois, and his primary appointment is in the Department of Material Science and Engineering. His research has been in the materials and the novel material patterning and making photonic electronic devices, and currently with the emphasis in the bio-inspired system. There are many publications, more than 300 papers. I should add that I often tell my students that Professor Rogers' publication has uplifted the quality, the entire standard of publication in physical science. I'm sure later he will show some example of his research result. He is a fellow of many society, IEEE, MRS, APS, and AAS, and he is a member of the National Academy of Engineering. And in 2009, he received the MacArthur Fellowship, and most recently, Lemelson MIT Prize in 2011. So today, he's going to tell us about the future of electronics, and so the title, okay, still the same title, yes. A stretchy, curvy future for electronics from neural interface to eyeball cameras. Yeah, welcome, John.
Okay, all right. Thanks very much for that kind introduction. It's a real honor to be here and have a chance to give this particular lectureship. So I thank Jung and also Larry for the role that they played in the selection process. Thanks also to the Mann family for making this possible. I'm listening to all the wonderful things you've done for Yale, and I'm thinking we need more alumni like that at Illinois. Yale's very lucky to have you affiliated with them. So I'll tell you about some research that we've been doing at Illinois over the last 5, 6, 7 years, depending on when you define the start date, and a future of electronics that we think could be interesting in terms of its ability to open up new areas of application and design engineering opportunities for electronics in a couple of areas that we think could be of broad societal value if we're able to sort of successfully do this sort of thing. And so as I mentioned, the title is The Stretchy, Curvy Future for Electronics, and we're interested in bio-integrated devices like neural interfaces and bio-inspired device designs like electronic eyeball-type cameras. And so I'll step you through some of the motivation, the concepts, and materials that kind of worked well for us in this space, and then give you a couple of specific examples of classes of devices that we think are pretty promising. But I'll just say at the outset, this is very much kind of a qualitative type of talk, and there's not a tremendous amount of technical detail. So if you're interested in more information and would like to talk further, I'd be happy to do that after the seminar. So I'll start with the motivation, give you a perspective of how this future of electronics sort of interfaces and intersects with the more traditional one. The classes of materials, mechanics, design concepts, assembly techniques, really sort of manufacturing approaches that are valuable, sort of an enabling component of that class of device, and then talk about brain surgery and epidermal electronics with a little live demo. So if you think about the future of electronics, most people think about, and most people are working on, a development pathway that was really established in the very early days after integration, the invention of the integrated circuit by Jack Kilby at Texas Instruments way back here in the early 70s. And it's a development pathway in which the number of transistors per processor is doubling every 18 months roughly. And that was a trend first spotted by Gordon Moore, and it's really remained true throughout the development up to modern times. And that's really a spectacular engineering achievement to sort of stay on that kind of scaling pathway. And because the overall processor size is not changing very much, what this means is that by increasing the number of transistors per die, you're really decreasing their individual sizes. And that is powerful because it allows you to pack more and more switching elements and therefore functionality per processor. And the other advantage of small is that for transistors, that means they can operate at lower voltages and switch at higher speeds. So the kind of problem that's being addressed by the research and development piece that's driving this development pathway is encapsulated by the statement that transistors are never small enough, they're never fast enough, and you never have enough of them. And there are all kinds of interesting challenges in material science, manufacturing, electrical engineering, physics that are needed to maintain this kind of scaling pathway. And I think that will remain a really compelling direction for research and for the future of consumer electronics into the foreseeable future. At least another 10 years of this looks feasible. And so that's a wonderful future for electronics, but it's not the one that we're interested in. We're interested in a different one that can coexist with that kind of electronics that addresses a different problem statement, where you essentially assume that the transistors are already small enough, you already have enough of them, and they already switch at high enough speeds. But the problem is that all known high-performance electronics are built on substrates that look like this. So this is a monocrystalline silicon wafer diced into various sizes. It's a wonderful platform for doing high-performance silicon integrated circuits because the material base is extremely pure. This is a very flat surface that allows you to do very precise manufacturing of the fine line electrodes that are needed for the devices and the interconnects and so on. But this platform offers up severe design constraints because it has the properties of a plate of glass, essentially. It's rigid, it's brittle, it fractures easily. You can't bend it, you certainly can't stretch it. It's also completely planar in its geometry. And you have silicon everywhere, even though you really only need silicon at the positions of the active devices. And a lot of an integrated circuit is not necessarily the switching transistors themselves. So wonderful platform for conventional electronics, but those kind of geometrical and mechanical constraints set by the wafer really prevent you from doing kinds of things that might be interesting. And for example, if you could reformat electronics into a shape that's stretchy, bendy, curvilinear, soft in its mechanical properties, then you might be able to do things that are impossible if you're constrained to that kind of wafer platform. And what are those things? You can imagine lots of things. Some of the more pedestrian ones would be a flexible display that has the look and feel of a sheet of paper, but it's a conventional display in the regular sense of the word. Or you can imagine the ability to bring that kind of soft, curvy electronics to bear on problems in human health by virtue of the fact that if you have a tissue-like form of electronics, then it can intimately wrap and integrate with the curvilinear soft tissues of the body in a very natural and very powerful way. So you might be able to build circuits that actually integrate with the surface of the body at the epidermis, for example, to provide advanced health monitoring functions. You might build an integrated circuit that can wrap the curvilinear soft surfaces of the brain to establish a brain-machine interface or to do diagnostics on patients who suffer from epilepsy, monitoring and also stimulation, deliver therapy in ways that would be impossible if you're constrained to this kind of rigid, brittle, silicon-based type of electronics, which is the more conventional established technology that's out there today. So this is what we've referred to as bio-integrated opportunities for a soft, stretchable electronics. But that's not all. There are other areas that we think are also interesting, where you look to biology for design inspiration in engineered human sort of man-made devices. And the concept there is that evolution has come up with all kinds of solutions to very challenging problems in technology, but none of those problems look like a silicon wafer in geometry or mechanics. And one good example is in the mammalian eye, where the detector surface is actually hemispherically curved, and that type of geometry, much different than a flat CCD chip that you'd find in a digital camera you can buy today, has advantages because it allows a very wide angle field of view with very simple lens optics for doing the imaging. So this is a big example of an electronic eyeball camera, man-made device that receives inspiration from biology. So these are a couple of different areas where we think breaking away from the design constraints set by the silicon wafer would open up new opportunities and new ways to deploy semiconductor devices and electronics. And this talk will really focus on these application areas towards the end. But before I get there, I need to step you through some of the ideas that allow you to go from plain or brittle silicon wafer-based electronics to these tissue-like bio-integrated systems that you see here today. And I'll show you physical embodiments of devices that do exactly that and this type of function. So how do you get there? You might think that if you want tissue-like electronics, you probably have to move away from silicon because silicon itself is a hard, brittle material. And if you do that, maybe you need to go off and develop completely new classes of electronic materials, maybe those that are based on carbon nanotubes polymers or elastomers or other kinds of materials. And that'd be one way to go. We've been interested in that over the years, so have a lot of other groups. I think there's a lot of promise in that approach. But from an engineering standpoint, you could make the claim that if you can do things like this with silicon, then that's probably the material set you would use, because you would be able to build on the incredible base of scientific knowledge that's developed around silicon as a result of the decades-long efforts around that material for more conventional integrated circuits. So that's been kind of our approach, to kind of revisit silicon and think about it from a mechanics standpoint and figure out whether it could be deployed for these kind of biointegrated systems. And so it turns out that relatively simple ideas in mechanics allow you to go from wafers to tissue-like electronics. And I'll mention two features of silicon in ultra-thin form on this slide. So if you think about a silicon wafer, as I mentioned before, it very much does have the properties of a plate of glass. You can't bend it very much, and if you drop it, it shatters. So that's one reason why it has that mechanics, is just due to the intrinsic properties of the silicon. The other has to do with the geometry of the wafer itself. The wafers that are used commercially these days have about a thickness of maybe 0.5 millimeter or 1 millimeter in thickness. And it's partly because of that large thickness that it has this resistance to bending and the inability to bend regardless of how much force you apply. And if you think about taking that silicon wafer and slicing it very, very, very thin, so take a silicon wafer and create from it a silicon nanomembrane, so a sheet of silicon where the thickness of that silicon might be 100 nanometers instead of 0.5 millimeter. And what happens is, by shrinking the thickness, you decrease by many orders of magnitude the resistance to bending for an applied force, and that quantity is known as the bending stiffness. It's proportional to the Young's modulus, the intrinsic properties of the silicon, times the thickness of the silicon, whether it's the wafer or this nanomembrane, raised to the third power. And that cubic dependence of the bending stiffness on thickness really provides a powerful lever for creating a flexible form of silicon from something that you typically sort of qualitatively think about as an intrinsically brittle material. So in fact, if you go from a wafer scale thickness of silicon, you have a bending stiffness that's about 10 Newton meters. If you decrease the thickness into this nanomembrane regime, you can go from 10 Newton meters in bending stiffness down to about 10 femtonewton meters. And that has a qualitative impact on the mechanical characteristics of the material. You go from a plate of glass to a floppy noodle, essentially, just by reducing the thickness. And the same concept, you can see, a 2x4 is a rigid piece of material. A sheet of paper is flexible. It's just by virtue of the fact that the paper is flexible, thin, that it's flexible. It's the same material. So the same idea here, very simple bending mechanics. So thin is floppy. The other nice thing about thin is that it's sticky, in the sense that if you take a sheet of silicon like this and you print it down onto a surface, in this case we printed a beam of silicon, sort of delivered it to a ridge that we've machined onto another silicon wafer. No adhesive here. It's just by virtue of van der Waals, very non-specific adhesion forces, that keep this piece of silicon tethered to the substrate at this one end, to the extent that you can keep this other part of the silicon suspended in a kind of a cantilever fashion. And the reason why the membranes stick so well to other materials has to do with the fundamental properties that drive crack propagation between two materials that you bring together in this way. And in particular, the propensity for forming cracks decreases, if everything else is held the same in the same geometry, decreases linearly with the thickness of the material. And in fact, for thermally driven crack formation, where the change in temperature of the system is driving cracks, typically differences in coefficients of thermal expansion will cause interface cracks to form, but the energy release rate associated with opening of those cracks is decreasing linearly with thickness. So that means the energy release rate when you go from a wafer to a nanomembrane form of silicon decreases also by orders of magnitude. So ultra-thin silicon is floppy and it's sticky. So it's floppy, that means you can bend it. It's sticky, which means you can take the silicon and you can put it onto a bendable substrate, like a sheet of plastic, and not worry too much about interface adhesion by virtue of this linear scaling down in the energy release rate associated with crack formation. So those are the interesting aspects of ultra-thin sheets of a material like silicon. How do you create it in the first place? And there are a variety of ways to do this. This gives one scheme that applies to classes of semiconductor materials that are currently used in lasers and photodetectors and wireless radio communication devices. It's gallium arsenide in this case. And it turns out that you can grow this gallium arsenide material on a gallium arsenide substrate in a special way, epitaxially in particular, that yields very high quality material. Now, if you do that kind of growth strategy in a way that alternates between aluminum arsenide and gallium arsenide, you can create a multi-layer stack of this kind of material, which is the semiconductor material you want to use in your devices, separated by this other material, aluminum arsenide in this case, which isolates those sheets of gallium arsenide for one another. And the nice thing about this kind of multi-layer stack is that if you go through and you etch down through the thin films that you're growing to expose the sidewalls, and you immerse this in a particular type of etchant, in this case hydrofluoric acid, it will etch away the aluminum arsenide selectively. That is, it etches this material a factor of 1,000,000 times faster than this material. And so after you grow that multi-layer stack, you etch down, you dip it in HF, and what you do is you release then from the surface of the growth wafer multi-layer stacks of ultra-thin sheets of gallium arsenide. And because you're doing this in a way that doesn't consume the wafer is sort of catalytic in this process, you can come back, use that wafer for another growth round, and really create enormous quantities of semiconductor-grade nanomembranes, in this case made of this compound semiconductor gallium arsenide, which is useful for high-quality, high-speed electronics, lasers, LEDs, and other kinds of devices. So here's how that looks in real life as a cartoon. This works extremely well. Here's an example of a 40-layer stack where we have 200 nanometer thick sheets of gallium arsenide separated by 20 nanometer thick layers of aluminum arsenide, etched down through that stack, immerse it in this hydrofluoric acid. That eliminates the aluminum arsenide. Off pops a lot of these gallium arsenide membranes into the solution bath, and then you can deposit them down onto another surface. You create bulk quantities of these kind of nanomembrane form semiconductor materials. And so each one of these little squares of gallium arsenide can serve as an active material component of a wide range of devices in electronics and other kinds of systems. But if you look at this, this is not really a very good starting point for an integrated circuit. This is sort of a disorganized collection of little membranes. So the question is, if this is your answer on the materials, like how do you grow semiconductor nanomembranes, it creates another problem, which is how do you organize them in a rational way to build an integrated circuit where the yields need to be 99.99% in individual devices. So one way to do this is just lift all the material off into the etching bath and then use some kind of strategic way to pattern the surface in surface chemistry or relief structures so that as this material sediments out of the etching bath, it drops down into specially defined locations on a target substrate, thereby preparing that surface for formation of interconnect wires to build a functional system. And that's an interesting concept in what is sometimes referred to as guided self-assembly. We're interested in that. A lot of other groups are interested in it as well. I think it's promising. The problem is to achieve the kind of engineering yields you need for doing realistic things is extremely challenging. So in parallel with those kind of efforts, we've taken a slightly different tack, which is that if you're creating this material from a wafer-based source in the first place, if you can design the system so that you undercut etch these nanomembranes from their underlying host substrate, but design lithographic structures so that they remain tethered to the underlying substrate in their lithographically defined location, then you can think of that processed wafer as an inking pad in a printing process that uses a soft stamp to pop off of the surface of those wafers selected collections of those nanomembranes, thereby inking them up onto the surface of the stamp, index the stamp over, this is all happening at room temperature and open air, and then deliver that stamp down to a target substrate of interest, could be a sheet of plastic, a piece of rubber, and drop off the nanomembranes from the stamp onto this target surface in sort of a massively parallel fashion that will allow you to come back and do this in a step and repeat type of mode to spread out this active material in desired locations on a foreign substrate. You do this as many times as you need, and then the next step in building an integrated circuit would be wire these individual membranes together to make a functional device. And so that's an approach that's worked extremely well for us. Now, if you think about how to make it work reliably, it's really all about understanding the physics of adhesion between those nanomembranes and the surface of the stamp. Because in particular, you want the adhesion to be strong enough you can pop them off the surface of this inking pad with high yields. But you don't want it to be too strong because you need to drop the membranes off of the stamp down onto the target surface where you want to build your circuit. So it all has to do with how do you modulate the adhesion strength from a high adhesion value to a low adhesion value in a reversible and controllable way. And it turns out there are a variety of biologically inspired routes to doing that, using inspiration from gecko feet. You can exploit the viscoelastic nature of the elastomer to accomplish that kind of switching. And I won't get into those details. We just mentioned that that becomes the focus of the science in making this engineering approach work, is really understanding the physics of soft adhesion so that you can manipulate the adhesion strength on and off to facilitate that process. So you can build a tool around that kind of concept. We work with manufacturing engineers in our Department of Mechanical Engineering to build a tool like that. There's a stamp here. There's an inking pad. There's a processed wafer here. There's a two-axis stage that supports a platform here. Corresponds to Gen 3 display glass. You can pick up membranes here using a stamp in this fixturing jig. There's a camera that allows you to look through the transparent stamp, so you can do registration and alignment, load cells over here, and it's all under computer control. So this can happen with very high throughputs corresponding to sort of about 1 million nanomembranes moved per hour with this kind of system with very good overlay accuracy. So this is what it looks like if you run that tool, use that kind of concept, create these nanomembranes in the ways that I showed you before. In this case, it's an array of gallium arsenide nanomembranes created in a densely packed configuration on the source wafer and then spread out at low aerial coverage in a step and repeat printing mode onto a sheet of plastic, which is what you see here, which is subsequently wrapped around a cylindrical glass support. So each one of these nanomembranes is about 250 microns on the side, about the size of a human hair roughly, 200 nanometers thick, and printed in this case is about 1,600 of them with 100% yield. So it's really demonstrating very high levels of control, both in the process as well as in the control of the adhesion for the assembly. So by virtue of the fact that the nanomembranes are sticky, they stay bonded to the plastic, they're flexible and floppy, so they can follow the curvature of the plastic in its bent state. And that provides a really exceptionally good starting point for making high-quality electronics, wafer-quality electronics, on a bendable sheet of plastic. And so I won't go into all the details of how you go about doing that. Just make the argument you have very high-quality semiconductor material on plastic. You can wire it up to make circuits and kind of leave it at that. And you can make circuits that are extremely flexible. So I mentioned before that as the thickness of a material goes down, its bending rigidity goes down. The surface strains associated with bending also go down. They go down linearly with thickness. So if you take those very thin membranes of semiconductors, put them on a very, very thin sheet of plastic, then you can make an integrated circuit with the properties of a comparably designed wafer-based device that are exceptionally flexible. In this case, wrapped around the sharp edge of a cover slip. This is a silicon CMOS integrated circuit, where the silicon layers, in this case, are sitting on top of a polymer sheet, where we select the polymer sheet to be very thin, but not arbitrarily thin, because we design the system so that the neutral mechanical plane is coincident with the most brittle layer in these circuits, which happens to be the silicon. If you think about the neutral mechanical plane, it's also a simple concept in mechanics. You have a sheet of material, and you bend it in this way, then the top surface is in tension, the bottom surface is in compression. For uniform material, the geometric midpoint sees zero bend-induced strain. And the neutral mechanical axis in this system is not the geometric midpoint, but you compute where it is. You overlap that neutral plane with the brittle silicon layer by choosing the underlying plastic substrate with an appropriate thickness to do that. So in this case, the entire circuit is just a little over 1.5 microns in thickness, able to bend a very sharp radiative curvature, about 25 microns in that case. At the same time, you retain sort of wafer scale characteristics in the individual switching devices and the integrated circuits you build with them. So if you look at the intrinsic mobility, it's about the same as what we see in a comparably designed device on a silicon wafer on-off ratio. The contrast and switching is very good. You can achieve very high frequency operation even with very coarse channel dimensions because of this very good intrinsic charge transport property of monocrystalline silicon created in this way. So that's a good step towards biointegration, but it's not where you need to go. If you think of a sheet of plastic, you can bend it around a sharp edge like that. You can wrap a cylinder or a cone, but you can't even wrap a sphere, much less a curvilinear body part. So you can wrap developable surfaces, but not undevelopable ones. And all of the human body is an undevelopable surface. So flexible is not good enough. The body is curvilinear in a way that you can't wrap with a sheet of plastic, and it's also stretchable in a way that a plastic sheet cannot accommodate. So you need something that goes beyond bendability to real stretching capacity. That is the ability to accommodate large strain deformation, not just bend-induced strains. And so you might think thin makes flexible. How in the world are you going to get to stretchable? And so we thought that that was going to be a daunting problem, but it turns out that that also has a very simple solution. And I won't get into all of the details, but just kind of give you a qualitative sense of it. So if you take this very thin silicon, as I've argued, it's very flexible, very bendable, can be bent a very tight radius of curvature. Now you take that silicon and you bond it against a rubber substrate that's slightly pre-stretched. After you bond it and you relax the pre-stretch, that induces compressive stresses in the bonded silicon. And the silicon, when subjected to those kinds of stresses on a soft elastomer substrate, will respond to that by undergoing a spontaneous nonlinear buckling instability that yields silicon in this wavy shape. These are strips of silicon about 180 meters thick, 10 microns wide, on an underlying silicone rubber substrate after that kind of process. And you can see this very wavy shape. And the first time we saw this sort of by accident, we thought, fantastic, that's exactly what we want. Because now we have sort of an accordion bellows made out of silicon, in the sense that if you take that underlying substrate and you stretch it out in this direction, the silicon strips can accommodate that strain in sort of an end-to-end displacement sense through changes in the amplitude and the wavelength of the waves. So as you stretch it out like this, the amplitudes go down, wavelengths go up. There's not much strain in the silicon itself, but you have an overall stretchability, which is what you're after. If you compress it, it does the opposite thing. The amplitude goes up, the wavelength goes down. So you can go back and forth like that, completely linear elastic response to strain, where the modulus is dominated by the stiffness of the underlying substrate. The silicon buckling physics allows it to move in a way that can move with those strains. So it's very much accordion bellows physics. Turns out that the details are quite important to understand, because in these kinds of systems, the mechanics design becomes as important as circuit design. So we're fortunate to be able to work with an excellent theoretical mechanician at Northwestern, and we work with him to develop finite element modeling and analytical models of exactly where the stresses and strains are in a system like this. And it turns out it's qualitatively different than an accordion bellows, but in terms of thinking about the physics, this is a good model, and we've sort of gone through the details of that. So in this case, this is just a concept. It's applied to strips of silicon. That's not an integrated circuit. And in fact, that is not a good starting point for an integrated circuit, because it's impossible to define the metal wiring on a soft rubber substrate like that. But the same idea can be applied chip scale. So take an optimized ultra-thin integrated circuit like this, bond it against a biaxially pre-strained piece of rubber, relax the biaxial pre-strain, and now you get a kind of a 2D buckling pattern that forms. It's a lot more complicated than what I showed you before, but conceptually it's very similar. So in this case, it's an array of 10 CMOS ring oscillators, 3-stage. There's some inverters down here and isolated N and P channel transistors up here. It's illuminated in a way that sort of highlights the wavy structure that forms as a result of that process. So you can imagine if you stretch this thing in any direction like that, those wave structures can change their geometries to accommodate that overall deformation without fracturing the silicon or the other components of the circuit. And so you have an overall integrated system that is dominated by the mechanics of the underlying rubber. So it's soft, stretchy, it's able to accommodate curvilinear deformations in ways that suggest an ability to integrate with the human body. And here's an image that was taken by photographers at our Beckman Institute. It's sort of nice in an aesthetic sense, but it also illustrates the physics. So we dropped off one of these wavy integrated circuits. They took a glass pipette, plunged it down in the middle, and what you see is that localized force causes this kind of deformation in the circuit where you end up with these curvilinear contours. And you can see this interconnect line, which was originally wavy and buckled in its shape like this one back here, has now been stretched out into a flat state to accommodate the tensile strains associated with that local force. So you can also imagine if you push this a little bit harder, that line would probably break, because it's been pulled flat. It can't accommodate much additional strain. So there's sort of a range of stretchability in these systems. It's about 15 to 20%. I'll come back to that in a second. So what do the properties of these things look like? This looks like, you've taken a perfectly fine integrated circuit and kind of crumpled it up, maybe destroyed it in some way. But it turns out that the waves are fairly modest in their amplitude. Few microns in amplitude, few hundred microns in period. So the actual strains in the materials are modest. And as a result, if you probe the individual devices, as being illustrated here, or the integrated circuit, the performance of this kind of device is pretty much similar to the comparably designed flat geometry. So you've achieved the mechanics you've wanted without sacrificing any of the performance. Now there are a couple of disadvantages, and I've already mentioned one. One is limited range of stretchability. So you can stretch these about 15 to 20% in a practical sense before things start to break. And that's just a constraint associated with the physics of buckling. The other disadvantage is that these devices are not fully isolated from strain. So as you stretch this thing around, the silicon is experiencing some amount of strain, and strain actually changes the way that the devices operate by a modest amount, 15 to 20%. And that's not important for a lot of the applications we're interested in, but if you're imagining building a very sophisticated integrated circuit, that might be a problem. So strain isolation and strain range are two limitations of this design. And both of them flow out of the fact that you're really at the mercy of buckling physics. You really haven't engineered where that wave structure has formed. That's just determined by the nonlinear mechanics of buckling. And so the way to avoid those constraints is to bring to bear better engineering control on that buckling process. And the way that you can do that involves two steps. One is taking the circuit and etching away parts of the material in the substrate you don't really need. There's no device there, there's no device there. You can just etch that into an open hole so that the circuit takes on the layout of a mesh, an open mesh. And furthermore, you design specifically which part of that mesh bonds with the underlying rubber substrate. Not everything should bond if you want to optimize the system, just selected locations. You can do that by tailoring in a patterned way the surface chemistry. And if you do those two things, then you can make systems that look more like this. So this is just a test platform. It's an array of silicon nanomembrane islands connected by polymer metal interconnect bridges that adopt this kind of non-coplanar arc-shaped design. So the entire system is in an open mesh. The nodes of the mesh correspond to silicon, where you can imagine populating those regions with devices. And then the interconnects in the mesh are not bonded strongly to the underlying elastomer. And as a result, when you relax that initial pre-strain, they pop up, delaminate, and pop up out of the plane. And so if you do that, you can create circuits that you can stretch maybe 100, 200%, much more like a rubber band, piece of latex or spandex, for example. And you do it in a way that really strain isolates the silicon. These silicon islands don't see much strain at all because the strain is being accommodated by these bridge-shaped interconnect ribbons, essentially. And so what these images are showing is you can take a circuit like that, and now you can sort of wrap it on any kind of surface you want. And this was just a demo. We took this silicon integrated circuit and wrapped it on the dimpled surface of a golf ball. So you can see that kind of golf ball shape. And you might imagine there could conceivably be applications of silicon electronics on a golf ball. And a lot of people have approached us with ideas about that. But we're not interested in that kind of application, but it does suggest an ability to take silicon and put it on the brain, for example, which is also a highly curvilinear surface just like that, to bring to bear to problems in neuroscience the full integrated power of silicon electronics. And that's what I'll talk to you for the rest of the talk about. So if you think about biointegration of electronics with the body, that field has a very long history, 40, 50 years. People have been thinking about putting electrodes on the body, shocking tissues, burning it out, injecting current, measuring things about the body. And there are a number of products that are already out there, FDA approved for various things, deep brain stimulators, for example, to treat certain forms of Parkinson's disease, pacemakers, of course, cochlear implants to restore hearing loss, all kinds of things. But if you look at all of the active electronics devices that are out there today, they incorporate this kind of design. So this is the example of brain stimulator, same thing for pacemaker, cochlear implant, all the other stuff. It's basically a separate box of conventional silicon wafer-based electronics at one position. Wires that run out of that box and then terminate at a few electrode point contacts at the tissue. In this case, these are wires that plunge down into the brain, and then the voltages that are pulsed onto those wires is controlled in a sophisticated way with the electronics back here. And although that can address certain problems in human health, it's a pretty primitive design when you think about it. It's not a very intimate integration. You have very limited numbers of electrode contacts that you can accommodate, and the electronics are totally separated. A more appealing way to do things might be to use design strategies that are present in contact lens, where the material itself is mechanically and shape matched to the tissue. It's gas and water permeable. It integrates in a very natural way. But the problem is it's not active. There's no electronics here. So basically reformat the electronics and look more like this for important problems, either on or in the surfaces of the human body. And so one of the most compelling places to think about introducing that kind of technology is at the neural interface of the brain. If you think of the brain, it's a very advanced electrical system, and if you want to study its function, or you want to perform therapy on it or monitor its function, the ideal thing would be to bring to bear to that problem man's most sophisticated form of electronics, which is silicon integrated circuits. And as I've mentioned many times, there's a huge mismatch in geometry, obvious one. Also mechanics, and I mentioned it a couple times, but let me just emphasize it. So the modulus, the stiffness of the silicon itself, is about 150 gigapascal. The modulus of brain tissue is about 5 kilopascal. So huge difference in geometry, but also in mechanics. And so, what do people do today? One thing that they do is build devices that look like this. These are Utah arrays. Very sophisticated devices have been used to advantage in neuroscience for the last 15, maybe almost 20 years. Spectacular piece of technology. It basically involves a flat platform where you can integrate silicon integrated electronics. Just take a chip out of that wafer, bond it up on here, and then establish electrical contacts between that integrated circuit and shafts of micro machine silicon electrodes that penetrate into the brain. So you put your circuit there, you take this thing, and then you mount it into the brain with an air hammer, and these pins penetrate down into the tissue. The tips of these pins establish the electrical contact to the brain tissue, and then you do stuff. You study brain function, you develop a brain-machine interface in that way. And that's fine, provided you're not doing it on a human. This is, and maybe it's not even fine, you do it on primates. Anyway, this is what's done. And obviously you're sort of doing some damage when you inject this thing into the brain. That's kind of an obvious one. The other one's not so obvious, which is that these are still shards of very high modulus, 150 gigapascal material against 5 kilopascal very soft brain tissue. And the problem with that is that the brain is a dynamic system. It swells, it contracts, it moves around in the head a little bit. And so that causes the soft tissue to rattle up against these very rigid silicon shards. And that causes irritation over time and continued degradation. So these things don't have long lifetimes when mounted up. So it's been a great research tool. It's a fantastically powerful thing and will continue to be very useful. But we're hoping the future looks a little bit different, where you create this kind of electronics to look like the tissue in shape and mechanics. So soft, shape conformal, biocompatible. The thing integrates in a very natural way and provides an intimate interface in that manner, using the kinds of ideas in mechanics, materials, and assembly techniques I described to you up to this point. So we've been working on that class of device the last 2.5, 3 years with experts at the Penn Epilepsy Center, University of Pennsylvania's medical school. They have experts in this area, clinicians who actually do surgical procedures to treat acute cases of epilepsy. And so this is what they do. And we're trying to configure our devices not to just be discovery tools for neuroscience, but something that can have clinically relevant mode of use in surgical operation. And so this is what's done today. Again, very acute cases. The patient's skull cap is removed surgically to expose the brain. And then you laminate on the surface of the brain these very crude electrode structures. They're basically solid metal pads embedded in a silicone rubber sheet, either in the form of a strip or a 2D sheet like this. Each electrode has a separate wire that comes out this way. The patient is only under local anesthetic, so they're awake while this is happening. All these wires are coming off of the head and then running to a computer. And what is done is a neurotoxin is applied to the patient to artificially stimulate a physical seizure. And at the same time, you're measuring electrical activity at each of these electrode pads, which are fairly coarsely spaced, about 1 centimeter on 1 centimeter, that kind of resolution. And you can't handle very much more because you have to deal with all these wires. It just becomes too cumbersome to continue to add electrodes. But if you do that, then a trained surgeon can tell from the spatiotemporal pattern of electrical activity recorded in this way which part of the brain is most intimately tied to the physical seizure. And once that's done, this thing is peeled away, and you go in with a scalpel, essentially cut it out, the aberrant region. And so in that kind of procedure, we are told that one would want, and it sort of makes sense, the highest possible resolution in that mapping, because you want to pinpoint the region of the brain that has to be resected. You don't want to take away any more than is absolutely necessary. So the idea is to go from electrodes to full integrated electronics in this kind of format for that sort of procedure. And so with the ideas that I described before, you can really ramp up levels of integration, very, very sophisticated systems. So this is an example of a 288 point measurement device for doing that kind of procedures. Over 2,000 of these nanomembrane transistors. It consists of an array of thin electrode pads on a flexible sheet. These laminate just directly to the surface of the brain. They don't penetrate in. It's just water capillarity sort of keeps this thing adhered to the tissue, almost like a piece of saran wrap on a piece of meat, for example. Each sensor has a multiplexing transistor and a local amplifier to boost up the signal levels. This is actually a device designed for cardiac, but the neural one is very, very similar. This is what it looks like. These devices not only have to have nice mechanics, but they also have to operate when completely immersed in salt water. Because when you open up the head and expose the brain, it dries out. So occasionally you have to flood the thing with warm saline. So your circuit cannot short out into the tissue when that happens. Very bad things will happen to the brain if that occurs. So the thing needs to be perfectly encapsulated and waterproof. That turns out to be a really practical difficulty because you need to do that without sacrificing the mechanics. So you need a waterproof layer that's thin enough that you maintain the mechanical flexibility. So I won't go into the details of that, but that can be done. So these things operate when completely immersed in salt water for extended periods. So let me show you an example of the device data that comes out of this kind of experiment performed on a cat model. So there's a colony of epileptic cats at University of Pennsylvania. And so you go through the exact same steps that I was mentioning before. Open the skull. In this case, it's not electrodes. It's full integrated electronics placed on the brain, apply a neurotoxin, stimulate a seizure, and watch what's going on here at very, very high resolution in terms of time and space. So let me show you a movie, what comes out of that. So this is what it looks like. So this is a spatiotemporal map. This is distance along one axis of that tape, other axis here. This is a representative time trace of a single sensor in that array. As a function of time, the neurotoxin is applied here. There's a lot of abnormal activity going on right now, but the physical seizure has not set in. That doesn't happen until about a second and a half after administering the drug. If you talk to people who suffer from epilepsy, this is a common thing. They can kind of sense that a seizure is coming on before it actually happens. And you can actually see that for the first time in this kind of measurement. Now the seizure is in full swing. And if you look at the level of periodicity in the response of a single point in this electrode array, it's quite remarkable. And that's reflected by this recurring spiral wave instability that you see across the area. And so this kind of measurement is unprecedented. It's never been done in a live animal model before because silicon electronics doesn't integrate with the surface of a cat brain, for example. So it's been done in brain slices, ex vivo, but not in a live animal model like this. So I think it's going to provide a lot of insights into fundamental neuroscience of epilepsy. We're excited about that. But I think the more important thing for us is it has this clinical mode of use as well. And this kind of resolution can't be achieved with those passive electrode arrays. So this is one thing that you can do now that was impossible previously by virtue of these simple ideas in mechanics, materials, and assembly that I've been describing to you. You can also do really wild stuff. So you can take these sheets and you can wrap them around a soft insert. Now you can plunge them down into hidden surfaces of the brain, say the gap between the right and left hemispheres, into the sul side of the brain, to really do high-resolution mapping on surfaces that are totally inaccessible using other approaches. And so we published some initial results in that kind of capability as well. So again, as a discovery tool, I think it's very, very powerful, and we're working with experts in this area to try to do something of value. Let me shift gears for the last part of the talk, last 10 minutes or so, and talk to you about another point of integration. So brain monitors, it's great. It's pretty much just for hospital use right now. And so if you want to develop a technology that's more widely adoptable by the general public, the skin becomes an interesting integration point. Skin's tough. It's interesting kind of material. It's soft, curvilinear, has all the kinds of challenges that the brain has in many ways, but additional ones. So if you think about what's out there today in terms of skin monitoring electronic devices, it uses the same basic design principle I outlined previously. Point contact electrodes connected to external boxes of electronics. In this case, the electrodes are affixed against the skin with an adhesive tape plus a conductive gel to facilitate low contact resistance coupling to the skin. Because you have a wire going to each of these electrode pads, you can only accommodate a few. Otherwise, just the practical difficulties of wires becomes challenging. So that's one constraint. The other constraint is nobody wants to wear this because this is uncomfortable. It's irritating to the skin. It's not something that's painful, but it's almost like Chinese water torture. It means the kind of thing that just creates incredible irritation over time. So it's great for maybe a clinical use, but nobody wants to wear that continuously, during the day. So it's great for some applications, others not. The slightly more advanced way to do things is take that box, crack it open, pull out the microchips, glue them to a tape, and then tape the device to the skin like that. And you can do that. It's maybe a little bit better. But still, the mechanics of the tape are not matched to the tissue. Again, flexible is not matching the properties of the skin. And so, as a result, it's an irritating interface. And people would rather not wear something like that either. So the skin is a unique system in the body. It provides our exclusive sensory interaction, sort of tactile interaction with the environment. And it's time dynamic and structurally complex in a way that the brain and the heart, for example, is not. The modulus of the different layers in the skin vary with depth. This is time dependent. It's a cellular escalator in a sense. Cells start here, they differentiate up to the stratum corneum, and then they exfoliate off. The thickness varies across the body, and you still have this curvilinear low modulus challenge to deal with. And it's really these characteristics that make it non-trivial to integrate even electrodes, much less electronics, with the skin. It's been historically a difficult problem. So it's hard to achieve, the interface is a problem, long-term viability with access. Adhesion is always a problem. Nothing sticks without irritation. Mechanics and shape are never matched. And of course, you have to worry about cost, power, weight, size, that kind of thing. So we've been thinking about that problem for about 3 years with this kind of vision, which is, a kid's temporary tattoo integrates with the skin in a really nice way. It's completely mechanically invisible. It sticks. It's low cost. It goes on a really simple way. It moves with the natural motions of the skin. It's completely non-constraining in the motion. Of course, it's not electronics. But what would it take to make electronics that look like that? So if you think about the geometry and the mechanics of a kid's temporary tattoo, very, very thin, 5 microns, ultra light, maybe 1 milligram per centimeter squared, very low modulus, matched to the epidermis ideally, but as low as you can go. 5 kilopascal might be a good target. Having some air and water permeability at the same time as achieving waterproof construction on the electronics. So you want air and water permeability in the regions of the electronics that won't short out due to the presence of water. So it's a little bit heterogeneous in terms of the waterproofing, but those are the kinds of things that you would ideally like to have. And so, can you do that kind of thing? And if you do, what is the key advantage? I think the key advantage is the fact that it goes on, it's mechanically invisible, and by virtue of the fact that driving the thickness of the modulus down to the levels that are comparable to the skin, you sort of solve the adhesion problem almost automatically without addressing challenges in new adhesives to the skin. And you can see that, and I won't go through the details here, this gets a little bit gory, but if you do mechanics modeling of a sheet of epidermal electronics on the skin and ask what happens at the interface between that electronics and the skin when the skin is stretched or bent, you can compute the shear stresses at the interface and the peeling stresses that tend to drive delamination of the electronics off the skin. And you can compare calculations for silicon chip, sheet of plastic, and skin-like construction. And what you find is that when you enter this low modulus simultaneously with low thickness regime, you drive those interface stresses down to very close to 0. Factor of 1,000,000 smaller than what you have to struggle with if you try to bond a silicon chip to the skin. And so that becomes a very, very powerful feature of the mechanics, and it really drives the design of the electronics into this sort of epidermal modulus matched regime. And you can kind of see that physics here. So if you just take a sheet of rubber and laminate it to the surface of the skin, you can see the effects of thickness and modulus even when the materials are exactly the same. So this is on the arm of a postdoc. It's a sheet of silicone rubber. Here it is laminated, and then the wrist is being contracted like that. And you can see you start driving delamination at the edges. The thing just flakes off. If you stretch it like this, again, edge-initiated delamination, the sheet comes off. If you do the same experiment, though, same material, just a slightly different formulation, so it's softer and thinner, then even without any adhesive at all, this is just laminated, just van der Waals forces against the skin, it's bonded very robustly. You stretch it as hard as you want. It doesn't come delaminated, and you can flex and move your wrist without causing the thing to peel off. And so it turns out you can look at that in a very quantitative way, and you can develop models for how that interface mechanics work, and I won't step you through that. Now, if you have arrived at a material that works in this way, the question is, how do you get a circuit on top of that without mechanically stiffening the system in a way that destroys that favorable mechanics? And it really comes back to ideas that I've already articulated, but implemented in a really extreme way. So thin, wavy, buckled, open mesh, but in this case, in the design of a filamentary serpentine structure. So very, very thin devices and structures in this kind of mesh, bonded to very low modulus elastomer. And if you do that, you can create an integrated circuit that has that characteristic. And then if you measure the stress-strain response, you find that this kind of circuit can be very quantitatively matched to the mechanical modulus of the skin. This is pig skin, actually, here. So about 160 kilopascal. And for this circuit, stretched along that direction or along that direction, the modulus is almost identical. Up to strains of about 20%, and then actually the modulus of the circuit is lower than that of the skin, but skin starts to tear above 20% strain. And you do all the FEM modeling, so you know exactly what the peak material strains are in that kind of design, and you can manage that in an effective way. Now the key thing is you can build all of your devices in that wavy snake-like geometry. So you can cut your silicon like that, you can make a transistor that's in this funny geometry, it still works fine. You can create strain gauges, even solar cells, photodetectors, temperature sensors, capacitors, inductors, LC oscillators, all kinds of components can be configured into that type of platform. And so if you take that thing, you laminate it on the skin, then it forms a very robust mechanical interface and in a form that naturally moves with the skin as it's deformed. So this is the postdoc who did the work, applied it here, and then we poked him in the skin with this pipette. You can kind of see it move like that. Now, if you peel this thing off, this is what it looks like. Ultra thin, floppy, very tissue-like, and so you can't manipulate it. It's just too floppy and thin. And so the question is, how do you, even handle this thing in order to mount it on the skin in the first place? And the way that we do that is just go back to kids' temporary tattoos, which oftentimes involve a water-soluble backing layer. And so we use PVA in this case. Laminate the epidermal electronics on top of that. Then you can use the PVA as a handle, slap it on the skin, and then wash off the PVA, just leaving the epidermal electronics on the skin. I'll show you a movie of that process. Here you can see it. So there's the piece. The PVA is facing outward. The silicon, the epidermal electronics is on the PVA, and it's being pressed against the skin. And what the postdoc is doing is they're just rubbing a thin layer of water against the PVA, gradually dissolving it away, leaving only the epidermal electronics pressed directly against the skin left behind. And what this circuit is really just a demonstration or a test platform consisting of an array of silicon transistors, an inductive coil, an RF antenna there, LC oscillators, strain gauges, temperature gauges, silicon diodes as well. So all the building blocks, I think, for a sophisticated form of electronics with integrated sensors, although it's not wired up to provide sort of system-level functionality. It's just a demonstration platform for those components. So once it's mounted up in that way, it's epidermal in its mechanics and thickness. And so when you deform the skin, you'll see that that circuit moves naturally in a way that really doesn't perturb at all the way the skin is moving around. So you can look at the way the skin is moving right in regions adjacent to the circuit. It's about the same as where the circuit is located. So it's really, by controlling geometry and layout, we can embed very, very rigid materials into an overall platform that has mechanics matched to the skin. And again, in this case, there's no adhesive between the electronics and the skin. This is one way to do it. I think for more robust integration, you may want to add an adhesive, but this is just a demonstration showing that by controlling the mechanics, you can really drive the stresses that would ordinarily lead to delamination down to very low values. So because there is no adhesive, you just peel it back. And so that's what's happening now. You can see this peeling away. The circuit's coming away. This is just dead parts of the, or unused parts of the substrate. You see this comes away. It's almost like peeling away dead skin after you get sunburned. I mean, it's a little disgusting at some level. That's what it is. So this is not multiple use, at least in this way. And then the sort of fun thing, you can actually use a temporary tattoo as a substrate. And that's nice because it's already a commercial, low-cost platform. So you put electronics there. This is a This is a custom tattoo, actually. This is the UIUC Pirate. Like Illinois has nothing to do with pirates, but we can't use the chief anymore, so we got to go with pirates these days as a mascot. So you apply it, you peel it back. Now the circuit is still there. You can't see it because the tattoo is not as opaque. So the circuit is sandwiched in between the tattoo and the skin, and so that the electronics is roughly coincident with the facial region of this Illinois Pirate, and you'll be able to see how that moves as the skin is deformed. And again, because the circuit is designed carefully in terms of the mechanics, the geometry, it's not changing the way the tattoo or the underlying skin is moving as a result of applied stresses and strains. So the circuit is there. Let me just, as soon as this squeezes, I'm going to just skip on by this thing. So you can deform it. So let's see that a second. Okay, so fine. You can see that it's not changing anything. So this is another experiment. I mean, that's sort of static deformation. We have a very high-speed camera at Beckman Institute, so we laminated this on a postdoc and then took a screwdriver and hit his skin right here. The postdoc wasn't fat, so he actually had to hit pretty hard in order to create a stress wave to come across that tattoo. But looking at the dynamics turned out to be sort of fun. I was told that this wasn't painful, but I can't verify that necessarily. But anyway, it moves up and down. It's moving with the skin in a dynamic and a static way without any problem. So the interface mechanics is great. So you can imagine doing all kinds of electronics on the skin. I think the most compelling applications are electronics that are talking to the body through the skin. So it's really not only the mechanics, but also the electrical interface. So here's a confocal image of that serpentine mesh at the crossing point. And you can see how it conforms to the rough surface of the skin. The skin is incredibly rough. It's a difficult place to mount electronics for that reason alone, forgetting about the modulus and the shape. But you can do that. And so we have procedures now that allow mounting sort of on the time scale of a week or so. And so I actually have a couple of these things mounted up on my arm right now. And I'll show you what these devices look like, because I have a really cool thing, which is a little portable microscope. So we'll see how this works. So it has illumination as well. So that's my bare skin. And no, I'm not a lizard. That's the way your skin looks up close like that. And so I've had these things on for a few days. I wasn't into body art, but now I'm totally into body art. I'm always like wearing this stuff. So this is a region of the circuit. You can look at different pads, electrodes, inductors, things like that. Very conformal to the roughness in the skin. So this is Gen 1. This is what was published in August. But just as Moore's law has a scaling trend, we have our own scaling trend, where smaller is better because of the mechanics, not necessarily because we're interested in high-speed transistors. So we can go much smaller now. So this is actually much finer features. You have to look a little bit closer, but you can see that's that filamentary serpentine mesh, fully conformal to the skin. The width of those lines is about 10 microns. You can kind of see it right at the edge there, the edge of the skin, and then you can see the electronics kind of following that tortuous topography. So these things are quite robust. You can take showers with these things on. There's no problem. So if you're interested in taking a closer look, I'd be happy to do that. Just my arm. Not too crazy. Anyway. So it's mostly useful because I think you get an interface to the body. Like you put your cell phone on here, but I don't think that would be very interesting. It's really sort of a medical application. And so we've demonstrated that you can do ECG, you can measure heart rate, heartbeat, even the detailed QRS patterns, very high quality measurements. You can measure EMG, electrical activity associated with muscle motion. If you compare the signal to noise to a conventional paste-on gel-based wire electrode, it's pretty comparable. But here you have full electronics. You can do densities of electrodes to arbitrarily high values. You have a lot of advantages in that sense. You can also measure brain waves. So you take this device, you do the chest, you measure ECG, do the arm, you measure EMG, put it on the forehead, and you can do EEG. And so the details here are not that important. It's basically just characteristic brain activity you expect to see with a normal EEG system. You can measure it here. And one of the interesting things is that there's sufficient data content in the EMG traces, EEG as well, to form the basis of a primitive brain-machine or human-machine interface. So this is an example where we took one of these epidermal EMG measuring systems, put on a neck. Again, it can go on the neck. You don't even know it's there. And then you can measure the electrical activity as you non-vocally state different words. So you just mouth different words, and you can create this kind of data set. This is a frequency spectrogram of EMG measured in this way. This is time along the x-axis. And you can see there are characteristic differences between different words. And we worked with Todd Coleman, who's a signal processing guy in ECE at Illinois, basically developed pattern recognition algorithms allow you to take this data and then bin it into a finite vocabulary of words. So this is just a baby step in that direction. So we can do 4 words. We can do up, down, left, right. But for someone who's suffering from a disease of the larynx or otherwise physically impaired, maybe this begins to hint at a way to do, human-machine interfaces. And you think about prosthetic control and disabled people. My students were mostly interested in playing video games, so we demonstrated it's a strategy game because it's all the pattern recognition integrated in software, so it's not fast enough to do shoot 'em up. But you can do a strategy game. So you move this cursor up, down, left, right, just using neck muscles to control the interface. So I think interfaces of that sort are interesting. But let me just conclude the talk with one sort of final image that you can take home with you if you dare to do that, which is another way that these devices can be used. So you can measure muscle activity, but you can also stimulate. So it's a two-way thing. So you can do both at the same time. You have an epidermal device on the forearm, for example. You can measure muscle contractions there. You can also stimulate them. And then that becomes interesting for physical rehabilitation. So we work with researchers, John McDonald and others at Johns Hopkins University, to explore that capability. So you now have epidermal electronics on muscle. It's not constraining the motion to follow it. And you can do this kind of stimulation in a feedback mode. So if you want to cure a muscle that's atrophied, for example, sort of stimulate it, that might be interesting. So this is a first animal experiment demonstrating that. It's an exercise rat, shaved hindquarters. This is a piece of, very primitive actually, piece of epidermal electronics, just as initial demo, that's stimulating the hind muscle quarters and also measuring EMG at the same time. So you can do some kind of interesting things in control, and this is just very recent work, but just to show that it's possible. So this device is moving with the muscle. It's causing the muscle to move, and it's monitoring that as well. So you can see this sort of move back and forth. And this looks pretty primitive. It's not quite as primitive as it may look because there's actually rotation right there and then a large-scale deflection. And so we're controlling those two types of motions by controlling the voltage and current impulse on these different electrodes and measuring the thing in closed-loop way. So this is a direction I think could be quite interesting, where you're doing both stimulation and measurement. So with that, let me just go ahead and conclude and try to give you a sense of why we think this is an interesting area. And what is appealing to us about it is that it really combines basic science with engineering in a way that could lead to things that are useful to people. That's our hope anyway. And there are all kind of topics, I think, that are out there that are, really, I think this is just very early days. Nothing is really solved here in the sense that materials and chemistry and physics and how you do adhesion control for the assembly and the mechanics and how do you think about the biotic-abiotic interface in these systems? Is active or passive? There's a lot of things that can be done here in basic science, but if you have a successful outcome here, it can map immediately into engineered systems that exploit that knowledge and advanced surgical devices. I show you a couple of things in neural. We do a lot in cardiac health monitors, wellness indicators, and then longer term, implants, BCI, and prosthetics control as well. So with that, let me just conclude by acknowledging some senior collaborators who work with a lot of different folks. I think it's been key for us over the years, mechanics, manufacturing, interface, chemical engineering. But the key is try to work with clinical folks so they can identify the problems better than we ever could. Brian Lidd in neurology, Dave Callens, Marv Schleppe in cardiology, John McDonald, I mentioned, Igor Efimov, also an expert in cardiology. And so we try to work on problems that they've identified as serious ones from a clinical standpoint. So sort of maximize the utility of what we're doing. But it does mean we have to work with those guys, and we have to work in their environment, which is kind of a new one for us. So this is Marv Schleppe. He's been a key supporter, involved in a lot of cardiac work, one of the world's most prominent interventional cardiologists, Starver Heart Center at University of Arizona, and this is part of his team, and this is the kind of world they operate in. So we deliver devices to them, and they use them, and we have a commercial channel. We're trying to make this stuff real and get it out there in a form that people can use, people like Marv can use over time. But the key thing is really outstanding students, and we're fortunate at Illinois to have a lot of them, and a lot of outstanding students here, but very, very hardworking students and postdocs. I want to conclude by acknowledging them and acknowledge you for your attention. I'd be happy to answer questions if you have any.